Alright, good morning, welcome back. Okay, so I just made this 2 videos just because like you might want a breather in between. We're looking at quantum number 2, which describes shape of elements. Alright, for our next adventure, we are going to draw a 3-dimensional shape on a 2-dimensional paper via digital technology. Okay, so I don't even have a classroom where I can like show you this stuff in like logical ways, blah blah blah. Okay, so we're all used to working with stuff that's not ideal. Okay, what I want you to do is I want you to find at least 3 writing utensils. So pens, pencils, markers, they don't even have to work. These could be sticks, I don't really care. But I want them to be, have the attribute of looking like lines. You're about to make a 3-dimensional graph in your very own workspace. Okay, I'm going to use these colors. I could use other colors, whatever. I'll swap this one out. Oh, I'll use the primary colors. There we go. Okay, perfect. Okay, so let's do this. I'm going to take this away and then bring it back, just so that we have a blank page to work on. Okay, so you go to math class, and you have seen a graph before, right? So you've seen your x-axis and your y-axis, and you've made 2-dimensional graphs on paper. Great. Okay, so take that in your brain, and what you're about to do is you are about to rotate an axis up. Okay, if I put my hand in the way, then you can't see it. So you're going to take this axis. Oh, this is great! Look at this light. Okay, cool. You're going to take this axis and rotate it towards you. And just think about that for a little bit. So, like, maybe you can take your paper and, like, fold it up. Yeah, you just did 10 minutes of paper folding in the other video. You can fold your paper up. And eventually, what we're going to start to see is this 3-dimensional graph paper. This is actually strikingly easy with a camera. Okay, hopefully. I mean, I hope it's also working for you. So these are the X and Y that you're used to. This axis right here, the one that I'm holding up with my hand, the yellow one, we call this the Z. You probably could have guessed that. And we describe it as going in and out of your paper. So, when we do whiteboard games, or if you have a pen that stands up on its own, we sometimes will just like plunk a pen down on your page so that you can get the visual of an axis coming in and out of the plane of your paper. Okay, this is like somewhat radical and a little bit mind-bendy sometimes. There's another way to think of it. I'm going to try this on here. Okay, so start by pointing at whatever is in front of you, and then add on, you know, this kind of shape. We're making these 3 axes with your hands. So right now, these are your X and Y. Take your middle finger, point it this direction. Hopefully this is helping someone. Maybe, who knows. So you're getting this like rotational 3-dimensional structure even in your own hand shape. The idea here is that you're starting to see the 3 dimensions as I guess unique, as graphable, as, you know, we're getting comfortable with a 3-dimensional graph instead of a 2-dimensional graph. Okay, on this video, I'm not going to spend that much time letting this sink in. This is the kind of thing where I usually give you some time to, like, wrap your brain around the idea of a 3rd dimension. Great, okay. Pause if you need to. Oh, I'll link that music video. That will actually help with the 3rd dimension. Good, good. Okay, so you now have a 3-dimensional graph in your brain. When we draw a 3-dimensional graph on a 2-dimensional paper, here's how we're going to do it. Here's the X and Y. Those are the ones that you're used to. Since we can't actually draw a line coming in and out of your paper, because that's not a thing that we can do, we're going to draw it as diagonal, like that. So you're kind of thinking of this as going into the page and this is coming out of the page, or vice versa. You can think of this as rotating. The music video will actually help in terms of seeing this. Okay, so these are three-dimensional graphs. The S orbital has, we just did all sorts of stuff. These are simple, these are a little complex, these are more complex, these are bonkers complex. Okay, the simple S orbital has one suborbital. The P orbital has 3 suborbitals. So, to draw 3 suborbitals, we need 3. 1, 2, 3. We need 3 three-dimensional grids to draw the 3 p suborbitals. Oh, but we're not done. You didn't think that'd be it, did you? The D orbital has 1, 3, 5 suborbitals. 1, 2, 3, 4, 5. The F orbital has 7, obviously, suborbitals. 1, 2, 3, 4, 5, 6, 7. Okay. Great. Good. Okay. So you are expected to know how to draw the S, the simplest one suborbital. We haven't even drawn anything yet, but you can figure out even from here that this is the simplest one. There's only one suborbital. So you want to know how to draw the S and the P, and you want to be able to recognize. And fun fact, I'm not even going to draw these at all, let alone on camera. I'll show you pictures of the F and of the D and the F. And so your questions here will say things like, look at this photo, tell me if it is a D or an F. Oh, I just realized those are grades. Duh. I've only been teaching this how long? Okay. Right. So I'll show you a picture. Tell me if this is a D or an F suborbital. This is an open note class. You can look it up. And we do enough like games in class that you get the hang of it. It's not so bad. And as you expect, the D's are somewhat complex and the F's are super complex, and that's basically what you look for when you're looking at a picture. Okay, but let's take us back to the simplest shape. You want to be able to draw this one. Get ready. You totally got this. Don't overthink it. That's it. The S orbital is the simplest. It only has one suborbital. It has the shape of a sphere. And it kind of makes sense. Hydrogen is up here. Bohr spent an entire career researching the one electron of hydrogen and came out with the Bohr model, which looks strikingly similar to a sphere. So, yeah, nailed that one. Earned that Nobel Prize. Okay, yes, so hydrogen does have the shape of a sphere, as do all of the elements in the S block. So the alkalis and the alkaline earths are the two groups in the S block, and all of those atoms have the shape of a sphere. Good. So when they react, their reactions are relatively kind of predictable in that way. We know exactly what they're going to do because their outside electrons only and always do sphere-shaped things. Simplest orbital, one suborbital, has the shape of a sphere. Okay. The P's You also need to know how to draw the P's. They're not super complex, don't worry. These are things like carbon and oxygen and nitrogen and like stuff that we use actually quite a bit. Most of the stuff you see around you is characterized by the shape of a p orbital. So even plastics are characterized by the shape of a p orbital. The only things that are not are things like your transition and inner transition metals. Okay. P's have the shape of, somebody at some point said petals. I like that. If we were together, you would be reading your textbook. It would tell you that P's are shaped like dumbbells. I don't think I've ever seen a dumbbell that looks like that, but great, you do you. Some kids think they look like eyes. I agree, they totally do look like eyes. Some people see Q-tips or like, I like petals because it starts with P and because it like references flowers. Okay, so P orbitals, like, and you'll see this in the video also, they have a petal-like shape. So these are the 3p suborbitals. The p orbital has all three, so your p's all together. Let's draw some form of showing you that this is something different. This is the p orbital all together. Has the px on the x-axis, and the py on the y-axis, and the pz on the z-axis. So if I drew that, you'd be like, that doesn't make sense. But, or, I mean, you might, like y'all are visual artists, you might be able to see 3 dimensions in that. We pull it apart like this so that you can see this p, let's do, yeah, okay, sorry, I had to think that through. Sometimes I do it differently, but for right now, let's say that this on the x-axis is the px, this on the y-axis is the py, this on the z-axis is the pz. So I might ask you to draw a px orbital, and what I'm looking for is the shape of a p on the axis, on the x-axis of the 3-dimensional grid. Great, okay. So that's how to draw your S and your P's. The other things that I'm going to leave you with here have to do with the electrons in the orbital. Okay. Here's your usually I make you think this through, but since I'm talking to myself, I'll do it. So look at your S block. The s orbital has one suborbital. Here's your s block. How many columns are in the s block? Answer: 2. Alkalis and the alkaline earths. There's 2 columns in the s block. This isn't going to work on screen. The big takeaway is each suborbital can hold 2 electrons. So your s block with a single 1 suborbital, that suborbital can hold 2 electrons. Your size 1 shape s orbital holds 2 elements. Your size 2 shape s orbital holds 2 elements. Your size 3 shape s orbital holds 2 elements. Your size 4 shape s, 2 elements. Your size 5 shape s, 2 elements. Your size 6 shape s, 2 elements. Hopefully that made some sense. We can try it with the p's also. You can rewind that if you want, but to keep the flow. Your p's have 3 suborbitals, 1, 2, 3. Each suborbital can hold 2 electrons, 2, 4, 6 total, 2 in each of these suborbitals. Your p block elements, if you count across your p block, you've got 6 elements. So on your second row, your 2 p's, size 2 shape p, 1, 2, 3, 4, 5, 6, can hold 6 electrons. It has 6 elements. Your size 3 shape p's. 1, 2, 3, 4, 5, 6. The 3 suborbitals hold 6 electrons. Size 4, shape P. Those 6 elements make sense. These 3 suborbitals can hold 6 electrons total. Your size 5, shape P. There's 6 elements there. 1, 2, 3, 4, 5, 6. It works for the D's and the F's as well. Your D's have 5 suborbitals. Each suborbital can hold 2 electrons. So already you can make a prediction about how many elements across in a row of the transition metals, because there's 5 suborbitals. Each can hold 2 electrons. In total, you've got 10 electrons in each d orbital. So each d orbital can hold 10 electrons. So you're 4 in the 4th row anyways. The D's, the top row of the D's, that orbital can hold 10 electrons. The next row of the D's, that row can hold 10 electrons, has 10 elements. All the rows of your D's have 10 elements. If you have a periodic table with a gap, that's really annoying because they should have printed something here. There's not actually a hole here. This is actually element number 71. Hopefully you are working with a table with no gap there. I'm not going to go deep on that. Because, actually, I am going to go deep on that. Your F's have 7 suborbitals. Each of those 7 can hold 2 electrons. Do some simple math. Tell me how many electrons each F orbital can hold. You've got yourself 7 times 2, 14. Each F orbital can hold 14 electrons. So count across your inner transition metals. Each row of your inner transition metals can hold 14 electrons, has 14 elements. So even if you've got this gappy thing in your table, down here where we've got row 6, you know, this is on the 6th row, and we're down here in the F block down here, count across, this should be 14. If you've got a gap here, what they did is they put the 15th down here. Really, your transition metals, this D block, this D orbital here, can hold 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. This F orbital can hold 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This 15th should have been printed there, because that's one of the 10 in this D block row. Oh, okay. So you'll notice that we just went through all of that stuff, and I haven't even touched the table that you folded yet. Because what we're going to put on the folded table is actually the size and shape together. We're going to merge them, and the merging is what we're going to draw on your folded table. So it's going to look kind of like this and kind of like that. And I'll get you that last step. Every element has a unique size and shape that its electrons hang out in. That we will call our Aufbau periodic table. We'll talk about that in another video.